Okay, so another effect of the magnetic field is the force it exerted on a current that is conducting carrying a conductor that is carrying a current. So let's assume, for example, we have a region of a magnetic field B that is pointing into the page, and there is a wire that is conducting a current, and this wire has a length L. Okay, this wire has a length L. So this wire will undergo a magnetic force. It will be given by F is equal to the current and the L in vector cross B. Okay, the cross product. Okay, so now some remarks. L is taken as direction of the current, as direction of R. This is very important. The direction of L is taken as direction of the current. So this will give us a way to calculate the direction of the force. So the direction of force is L cross B, and since the L is taken as the magnetic as the direction of the current, the direction of L is taken as the direction of the current, so then it's clear that the force will be upward. The force will be upward. Okay, let's give an example. And this is a very important concept that is used in power systems, in electrical engineering a lot, especially in power systems. So let's give us an example. So this an example. So let's take a triangular loop. This triangular loop has the following. Let's say I have a triangular loop that have the same. So so this is side one. So the triangular loop is crossed by a current, and this current is the same, is I, and side one is here, side two is here, and side three. So side one and side two, they have the same length, L. So side one and two, they have, each one has a length L. And now, so this is X, Y, and Z, and I apply a magnetic field B, and this magnetic field, it has, as you can see, it's in the opposite direction of the Y, the positive axis of the Y axis, positive side of the Y axis. So I can call it as minus B0, okay. And the question is, what is the force exerted by the magnetic field on each side, 1, 2, and 3? So the question is the magnetic force on each side. So let's start by side one. Now, the magnetic force F1 is equal to I, because it's the same current, L1 cross B. Now, I know that the direction of L1 is taken as the direction of the current I. And so this gives me L1 is equal to Li, because the current is going in the positive direction of the x-axis. This is the x-axis. So Li. So if I replace, this will give Li cross minus B0K. It's equal to minus I L B0 I cross K. Okay. Now I cross K is minus J. So this means that the force on one, the force on side one, so the force on side one will be equal, minus minus goes to a positive sign, I L B0 J. So the force on side one will be across, this is F1, okay? Now, what is the force on side two? The force on side two, again, is equal to F2, is equal to IL2 cross B, but we know that L2, the direction of the current in side 2 is, so the direction of the current in L2 is LJ. So L2 is equal to LJ, right? So this means that I can replace it ILJ cross minus B0K, and this gives a minus sign here, IL B0 and J cross K. Well, J cross K gives I. This means the force on side 2, the force on side 2 is equal to minus I L B0 I. Okay, so the force on side 2 will go to this way. Okay. Now, the interesting part is side 3. Now, again, the force on 3 is equal to I L3 cross B. Now, L3 is in the plane of X, Y. So L3, if you take X is this way, Y is this way, L3 is here. This is L3. So L3 has an angle of 45 degrees. Why 45 degrees? Because the triangle that is formed between side 1 and side 2, this is L, this is L, so it's an angle, a triangle that has 45, and this is a 90 degrees. So it has 45 degrees, and this means that L3 must be written as a component along, component along X, I plus a component along Y, J. I mean, this can easily be calculated, and you can find that it's equal to minus L square root of 2 over 2 I minus L square root of 2, so L3, sorry, L3 square root J. Now, in addition to that, we know that L3 is equal to, from the Pythagoras theorem, is equal to L squared plus L squared. Okay, this is the hypotenuse. So which means L3 is equal to L square root of 2. Okay, so let's go back to F3. Or we can already replace first. So L3 becomes, so minus L square root of 2 times square root of 2 over 2I minus L square root of 2 times square root of 2 to J. So L3 becomes easily minus Li minus Lj. This is L3. Then we replace in the force F3. So F3 is equal to I L3, which is minus Li minus Lj cross minus B0K, the magnetic field, okay, from this equation. So we can split, okay, so we can split, this will give as I L B0 I cross K, the first part, okay, and then plus I L B0 I L B0 J cross K. Okay. So I cross K gives as minus J. J cross K gives as I. Okay, gives us I. J cross K, J cross K gives us I. So the final force on F3, on L3, the final force L3 is equal to I L B0 I minus I L B0 J. So this is the force on I3.